So hello everybody and welcome to another video. It's quite some time since we had another video, and I guess almost a year ago. But one of the latest videos was basically about the RAG, so Retrieval Augmented Generation, and how you can run this on your machine at home. And this video was rather successful, so I was thinking a bit, the problem with this video is that yeah, you know how to run it at home, but you don't know really about the engine behind it. And so in order to get a bit more into detail, I thought we can do like a course where we have a RAG and we implement it by hand in Python. And this is what I want to do here. So I want to do a basic RAG in Python with you from scratch without using any fancy libraries like LangChain and so others. Let's go a bit about the theory first so that you know what we're doing. So just a quick recap, what is an LLM? So an LLM is a large language model. This is something that you're all using when you use like something like ChatGPT. And what this basically does, it generates tokens. Yeah. It generates tokens, and in order to generate token, it has to have a prompt before it. So it's just like a completion story. So basically what it does is you give it a prompt and it completes the text that you have given to it. And due to very intriguous control tokens, you basically can manage a conversation. So you have this kind of end of turn token. So let's say you ask a question. After this question, some kind of end of turn token comes. The LLM continues the text. As it continues the text, it answers the token until by its training it knows, okay, I should stop here, and my part of the conversation ends, and it spits out this end of turn token that it was trained on to say, okay, my answer stops here basically. How this is constructed is basically dependent on the LLM, on how the LLM was trained, how this kind of instruct models, so in general these conversational models are called these instruct models, which use all these kind of control tokens, are trained on, and we will dive a bit into the depth of how this works, for instance with Llama 3, or in general with most of the Llama models. So in general, what does this chat template, or what do the control tokens in Llama 3 look like? So you have kind of some kind of system message, we have some kind of user message, and we have some kind of header message here, where basically we can play with the RAG. So basically we can tell in the system message, well, how does the LLM behave? This is kind of part of the prompt engineering. We can say, okay, you should talk in the language of a 5-year-old, or you should talk in the language of a professional medical doctor, something like this. Of course, we can also use in the system message basically the documents that we want to have in the RAG. So the RAG is basically you want to have documents that are not inside your training set, inside the training set of the LLM, and you want to converse about these documents. This can come from a database, this can come from anywhere else, this can come from, this can be a web query basically, and you can kind of insert this into the system prompt and say, look, for instance, here you have 10 parts of a thesis. Answer me according to these 10 parts of the thesis. And only, for instance, you can also kind of limit this. You can say, okay, only answer if the document basically is contained within these 10 parts of this thesis that I give you, and otherwise don't answer in order to provide hallucination and things like this. Yeah. So as you see, what I want to go into here is basically we have these constructs here. So these are kind of these tokens. So it says here the start head ID and in this system end head ID, and so it knows, okay, this here is the system message when it digests the prompt, and this here is the question. And in general, what you do during the RAG is, well, you use this user message in order, when the user basically types it down on an interface, in order to build this prompt message. Yeah. And then in the end, we have this assistant message. So the assistant message basically is what the LLM yields. And why do I need this in the prompt? Because I want to keep the conversation going, and I want to know about the history, basically, of the text. Yeah? So the LLM, as it's just a token generator, it has no memory, yeah? So it can't really know what it conversed about before. And how does it know what it conversed about before? Because we tell it in the prompt, look, I said this, then you said this, and right now I'm answering another question. And so this is all done by the prompt in general, so we have to take care about the history of the of what we asked, and we also have basically to take care about the context that we find somewhere else if this is not in the training data of the LLM, or if we want to build basically a RAG, which is kind of the story of this video. Yeah. Okay, so far so good. Let's see how this looks a bit in practice. So as I said, well, we have this client supplied part here. So basically we of course we provide the system prompt and we provide the user message. So as I said, in the system prompt, what will go in here? Well, the behavior of the system, so of the behavior of the LLM, in what kind of language it should basically answer. And we can provide some context. So the RAG is basically finding these contexts. This is why it's called retrieval augmented generation. So we find the context in external databases, we put it here in the system message, and we converse with the RAG. Okay. In general, these external databases are vector databases. We will talk about this a bit in a moment. And then the model basically provides an answer here, and we keep, of course, this question, this answer also, so that in general that we then can have a history and can talk basically, can ask another question about the answer of the LLM. Yeah? So how does this work in practice? So the inquirer basically, he writes this user message that we have here. So the inquirer is a basic user. This is what you write in your ChatGPT web interface if you want to, something like that. And then how does the RAG work? So the RAG, it searches, as I just said, for related texts of this user message. Yeah? So we use a database, we do a web query. In our case, we will use a vector database. We will build a vector database, and we will try to retrieve basically texts that work that according to this user message. So you search for context to the user's question. Yeah? This is where vector database comes very handy. As I said, why I want to do this, because basically you have probably in your company in-house data that you don't want to train, or that the LLM is not trained on. You might basically want to build a chatbot which is kind of where you want to tightly control the language of the chatbot, for instance, for children. And you want to say, look, if in my database of provided documents that you provide to this chatbot, you don't find the answer, then don't answer, so that the LLM doesn't come up with an arbitrary answer that you might not predict. Yeah? These are things that you can use the RAG for. There are many other topics. These are just some use cases. Also, the typical use case that we will do here is chatting with a document. Yeah? Okay. Then we have basically the retrieved, so as we say, this retrieved related text. So we search for documents according to this query, and we add this retrieved text basically into the system prompt. Yeah? So how do we do this? So as I said, we add here, look, answer, the user asks this question here, and then we say basically answer according to these documents that we have found. Yeah? In the prompt in general, the user message comes after the system message. It doesn't matter because we can build it all at once. So we will first parse the user message, then we build the system prompt, and then we build the whole prompt that we then provide to the LLM so that it can basically answer. Yeah? That's the way it works. And then, of course, as said, basically once we have this system prompt and the user message, well, then the LLM starts generating tokens according to what stands in the prompt until basically this end of turn token comes, and then in order to continue the conversation, well, we put another user message afterwards and another assistant message afterwards. And you can imagine that you can also always kind of change the system message and retrieve new documents or something like this. This is not what we will do in this sample, but we will just once basically retrieve a document and according to this document pose questions and answers, and just extend basically with user assistant messages the prompt in order to keep the history. Yeah. If the history of the prompt basically becomes too long, you can also say, okay, I want to summarize basically the whole story so that it fits basically into the context of the LLM. So the maximum size of this prompt is of course limited by the context size of your LLM, and therefore at a certain time either you cut basically the history off, or you kind of let your LLM summarize it or compress the whole chat time, so basically this whole prompt in different ways. Okay, so how it works in practice. So as I said, basically you type a message, a database is inquired somewhere, it finds related documents to your system, and basically a complete prompt basically is built from these texts. Yeah? Okay, so what does a finished prompt like this look like? Just to give you an idea, so this is kind of a prompt that you can send to an LLM, and then the LLM basically, so your prompt would start here after this end header ID basically, and as I said, the LLM, then it's just a completion system, so then it kind of spits out the tokens which makes up these words here until at a certain point, end of turn ID token from its training comes up, and then it says, okay, I stop here and I wait for another question, okay, because the LLMs, they're basically trained by conversations like this with these tokens inserted, and so it knows, okay, what is the next token, what is the highest probability to spit out this word here, but not only this word, so instead of a word, then it spits out this end of turn ID token that was part of its training set or of its fine-tuning set, and then it knows, okay, right now it's my turn in order to write a question. Yeah. In order to do the reg, so what we see here, basically we post this question here, write a report about new services. We find basically these documents that correspond to the semantics of this question, and we insert them here, and we write something like, okay, here, as I said, we define the behavior of the chatbot, so this should be a kind chatbot which should answer the user's questions, and it should, of course, the contexts that we found, this is the reg in our local database, to take them into account. Yeah? So here basically we add the context, and then we have this whole basically prompt here, and we say, okay, look, and then the LLM generates from this prompt basically the answer. Okay, so in order to do the reg, there's a big question about what is semantically similar. Yeah, and in general, this is answered by vector databases. Okay, we will not go into all details how to verify everything here. This should just give you an overview about how to use the reg, how to do all these things. What do we have here? So in general, how do you find this related data? So what most of the people do is they use vector databases and embedding models, and this is what we will also do in this video. There's also people use, you're not limited to this, you can use relational databases, you can use graph databases, you can use basically search systems, so web search systems, you can use Apache Lucene and other tools basically to search your local data in your enterprise and say, okay, I want to have this kind of text in my prompt and answer according to this text. Yeah? All straightforward so far. The next big question basically is, if you have this vector database, so what is semantically similar and how do vector databases work in order to find semantically similar contexts? And this is kind of also the art of the RAG, yeah. So finding the right context is always a bit tricky, as you can imagine, because the user asks us like one question, and you can't rely on the LLM in general. That's why you built the RAG, in order to answer this question. So you add some context to the question that you find in a database. And in this database, basically you want to find semantically similar text. So texts that kind of have the same meaning, or that are at least related to the question that you want to have. Yeah. And so, in order to do this, we use kind of specially trained neural networks, so-called embedding models, which provide us with this vector comparison index, which is basically called the embedding. So what are these embeddings? How does this work? So let's say I have a text here, and I say, okay, the mother searched children at the school, and then I get an embedding out here. And if I have another text and say, okay, the mother searched the children at the kindergarten, which is kind of, let's say it's semantically close, we get an embedding that is kind of close, as you can see it here in these embeddings. This is kind of the story. So you want to have semantically similar text should yield semantically similar embeddings. Yeah. Let's give me a counter example, so where it gets a bit more tricky. Let's say I'm staying at home today, or I'm going out today, and the other phrase is I'm going to the cinema today. Yeah. So if I have this, basically I'm going out today should be closer to I'm going to the cinema today than I'm staying at home. Yeah. This is kind of the story here. Here it sounds semantically similar, but let's give me the counter example. Let's say I'm staying at home and I'm going not to the cinema should be semantically similar than I'm going to the cinema. Okay. And here it's kind of difficult in order to find this context. So this is why we have these special embedding models, which are neural networks by themselves, and which most of the time also use transformer models in order to kind of capture these contexts and find semantically similar texts. Yeah. So we then use a vector database. So a vector database is basically an index for all these kind of texts with these kind of embedding vectors, and then we can kind of compare a query to these embedding vectors, and by comparison of these embedding vectors, we can then find the right context basically to the question that we have, and insert it in the prompt as I've just shown you before. Yeah. This is the whole story behind the RAG. Yeah. And how to retrieve basically the data in the vector database. So basically I pass the question here, and I say, did the mother search her children at the school? And then basically I have this kind of question, and I'm looking for a similar text, and I will find, okay, well, hopefully I find the right answer. So I find basically the embedding in my vector database where I have all these kind of contexts, and I find, okay, the mother searched the children at the kindergarten. And how do I do in general is this done? So in general you use of course some kind of function in order to compare these vectors, yeah, because you search basically the closest vectors, and the closest vectors should be those who have the highest semantical similarity. Yeah. And this is done in general by the cosine similarity. So the cosine similarity is nothing else than the inner product basically. If your embeddings are already normalized, you can just use the inner product. If your embeddings are not normalized, you have to normalize these vectors here. And then you get this cosine distance out. And in this case, I mean, this is the way how you write it. Normally, the cosine distance, you write it with 1 minus what is written here. Because in general, of course, the closest vector should be 1 if the inner product, basically, if they point into the same direction. If they point in a different direction, then we hope that these embeddings are semantically not similar. If they point into the same direction, then they should be semantically similar. And we could even say that they have the opposite meaning if basically -1 comes out from this cosine similarity. Yeah. And we can, of course, write this. So in this case, basically, we search for the meaning set that the closest to 1. Yeah. in general, what you do is you want those the closest to 0, so you write 1 minus this, and then basically you can say, okay, if it becomes 1, and if in the worst case, even if it becomes 2, then you basically, these are the ones that I want to avoid. Yeah? That's the whole story behind this. That's as easy as this. And then we go quickly into a practical setup. So how can we set this up? So we need an LLM server, we need an embedding server, and we need basically a program, and this is what we will later on write in Python for all this. Yeah. So basically we have a REST API. This is LLAMA.CPP, basically is a nice engine in order to do this. We need a LLM basically for this. We need a large language model that we need to download the Hugging Face somewhere. The same, we do this with the embedding models. We also need to download the embedding model. And we also run this with LLAMA.CPP, and then we both can query basically LLAMA.CPP through an API. This is the same API that also other AI service providers basically provide. So you can buy credits, for instance, at OpenAPI, and use in the same way their API in order to build your RAG model, and inquire OpenAPI as an LLM and as an embedding model, and work with your own documents. But then, of course, your documents leave your enterprise. With a LLM setup, as I will show you here, this is not need to be the case. You can basically run your own server somewhere in your enterprise if you have a GPU, even for several users. Here we will do this on my little laptop as always, and basically we will just use the LLM as a text generator, so it's not so important that the LLM is so efficient. And we can use rather small models in order to build this, so that you basically get an idea of what's going on here. Basically what we will do in our tutorial is we will talk to a local PDF. We will use LLAMA.CPP, as I said, as the LLM engine, and then we will write some Python code in order to do this. Yeah? Both the LLM and the embedding model have limited context sizes. You always have to take this into account when you build your RAG. In general, the context sizes are rather large already for the LLMs, not so large sometimes for the embedding models. The story is, you can say, the context size is, of course, how much you can put into this prompt, as I said it. So how much context you can put into this prompt, also how much history you can keep from the prompt, because the prompt gets, of course, larger and larger as you ask questions, etc. So it depends on how much data you can inject here, and there are, of course, today models that have like 128k tokens of context size and more, so I can put a whole thesis basically into the prompt. But then sometimes this model use large amounts of memory, and the memory in your GPUs might be limited. And also it takes a lot of time in order to basically process the prompt. And this is all things that you want to avoid, because of course you want to have a quick answer for the users of your RAG system, and you don't want to have them wait half a day in order to get an answer. So you're always kind of limited with the context size, so how large this prompt can be. And so the story here is basically what to do. So we will basically, here we will talk to a local PDF file. We will talk about the scientific article basically. So a PDF file that we have converted into text, and then we will talk to it. And how we will do this, basically we build slices of texts from this PDF file. And these slices, this is where this vector database comes in handy, because each slice basically will be indexed in the vector database, and we just search maybe for 5 to 10 slices in order to give the answer to our to the question according to the context, in this case a PDF. So we can build an engine with this RAG, talk to a local PDF. This is what we will do, and we will show you how we can do this. So how we build up, so I guess this is kind of the same setup as in the last video, but just that this time we really write the code. We just don't download the LLAMA.CPP, basically my C coded up RAG system. We will really basically use Python in order to build this, and I will show you how you can do this. Yeah. So we will have a local vector database. We have the local client. This is basically what we write. We have a local document, as I said, a scientific article that we will use, which we basically want to use as a context, and we want to talk to this document. So you see these services basically come up on the internet. You have this talk to the document services, and we will allow to talk to a document. We will have this document basically processed by the local client in order to build the vector database. So this is kind of the first step. So we feed this document to the local client. The local client will build these text slices basically, and it will query with these text slices an embedding server. And the embedding server will yield these embeddings that we store in the local vector database together with the text, so with these text slices. And this forms kind of the index of what kind of context we want to have given the query of the user. Yeah. So then here it looks a bit more complicated, but what happens basically when I ask a question? So when I ask then a question to the system, the local client also queries the embedding server first. So it builds an embedding from the question that I've built. Using this embedding, it performs these cosine distance measures on all the text slices that I've stored in before in the local vector database. It finds the closest text according to this embedding. With this, it builds basically this whole context. So the contexts that I insert into my prompt. From all of this, we build a finished prompt. The local client does this, so it takes this context into account. And when it did this, basically, we have the context, we have the finished prompt. The finished prompt, as I have shown it to you before, this llama prompt with everything inside, with the user message and the context given and the behavior, of course, of the LLM. We send this to the LLM server, and the LLM server then gives us the answer, of course, the answer to the question. And then we can continue, basically, the conversation, because we stored the history, and continue the prompt and build the whole thing. You will see this how this is done basically in the coding session. And then basically, of course, the RAG is an active research topic, so there are many ways how you can do this. So there is several things that are currently done. So there is network science. There are several things going on. We will not go into detail in this coding session, but just to give you basically an idea. There are things, so for instance, how can you secure factual answers? As I said, you can basically, using clever prompt engineering in the RAG, you can say, look, you only answer if you find the answer in the documents that you have retrieved in a vector database or in my local database of my enterprise. And this way, basically, make sure that there is no hallucination going on, and that it basically it gives the answers that you want. Yeah. This is kind of the story here. So how can you do this? For instance, we will show you a bit about this factual answers. So basically we have our prompt here. These are the retrieved documents. And basically we can say, okay, let's only answer if basically the answer can be found in these contexts, in these provided contexts. Yeah? And hopefully the LLM then basically always have to test this. But hopefully the LLM answers as you like it according to the behavior that you have written here in the system message. Yeah? We can also do some kind of self-reflection just to have an idea. Several models, they are right now trained with this inherent self-reflection. So this means they provide it with prompts during the training process where kind of this self-reflection is already inside. And they use special tokens in order to do this. So they use like a sync token, something like this that we don't have here, but you can even kind of program this yourself. So you can say, look, you take this answer that comes out here, and without writing here this assistant message, you can kind of feed this backwards into the system message, for instance, and say, look, in a first run you provided this answer. Think about it and provide, if this answer is correct, and provide a correct answer, a best correct answer. And then you just yield the second pass, and hopefully you come up with, then you can test this, and hopefully your LLM comes up with better answers than in a first pass. You can say it like this. Yeah. this is questionable, but this is what people do, and you can kind of build the RAG with self-reflection this way. Yeah? Okay, then there are also evaluation benchmarks. We will not go into all the evaluation benchmarks, but the idea is basically when you build these systems, you also have to evaluate them. You have to evaluate them for your use case. In general, at least for these embedding models, there's this MTAP benchmark. So where you have a leaderboard on Hugging Face, and you can say, look, this is the best embedding model. I want to use this embedding model, and of course, there's a trade-off between the speed of the embedding model, because the best embedding models maybe are not the best in runtime. So how much energy do you want to use? How much computers do you have available for your system? If you have 1,000 of clients to your system and you use a very large embedding model, then this costs you a lot of energy. And you might use a lesser embedding model that just suits your use case, and that's why you have to test this. Yeah? There are several ways to test this. We will not go into all details. Maybe we do this in another video. In the next step, basically, we want to code this up, and we want to have our basically our RAG model. Yeah? So what I will do basically in the next step is I will download a PDF from the internet, and we will try to talk to this PDF. So as pointed out, we want to do basically here the practical implementation of the story of the RAG, and in order to do so, first of all, we need a document. So a document that we will use the article basically that I've written one day, or an article that I've written one day, which talks about COVID. So if one searches my name, and this was published in Infectious Diseases, one finds this article. No worries, this here is in German, but here the article basically, this is this article here, respective analysis of SARS-CoV-2 Omicron invasion. And we will use basically this article as the basis of our RAG. Yeah? So what we want to build is a talk-to-F document type of system, and we will use this article basically as the basis for that. So how we will use this? So basically we download the PDF of this article, and then we have to convert this article to text. So I download the PDF here. Then I have to convert it to text. So how will I convert it to text? Our text conversion is not very elaborate, it's very simple. We have this here in downloads, and basically with the Poplar library in Linux, if you want you can search it, it's like written like this. So if this library basically comes with a tool which is called PDF to text, and this PDF to text tool, we will use it in order to generate text from this PDF file. There are way more elaborate stories on how to do this. There are today LLMs basically that can describe you the images of the PDF and things like that. Here, in order to talk to this PDF, we just use a simple PDF to text conversion. In a more, let's say, in a more elaborate setup, you might use something more elaborate. Here, for simplicity and for speed of implementation, basically we just recurse to this tool here. And I do this, and as I do this, I get out the text file, and basically you see it here. This is my text file here. I will also enable here on my machine basically to speed it a bit up. As this is my tiny laptop, because we need to run right now an LLM, and we need to run, as pointed out, an embedding model. And in order to do this, we will use LLAMA.CPP. For those who don't know LLAMA.CPP, basically, let's again go to the web. So we have here the web. This is the article that we talked about it. So basically, LLAMA.CPP, you will also find it very easy. So you just search for LLAMA.CPP, and it's this GitHub page here. And as we go to this GitHub page, basically you can download here, and you find all the install instructions, how to install it, and maybe you find something for your distribution. I'm using here again to distribution. You can just compile it. I have this installed here on my machine already. without going into any details how to install this, I guess there was also a previous video how to do this in this old video, how to run your reg at home, where you kind of see how to compile LLAMA.CPP maybe. Here we have it basically installed, and you also have basically the models here installed. So if I go here to, I stored them in my computer under Xdata LLMs, and basically I have two models. I have the all mini LLM L6 V2Q, also in 8-bit quantization model. Let's maybe find this on the web. So basically these ones, they're downloaded from Hugging Face, so you can go here to Hugging Face. And in Hugging Face you can search for this model. So if I search here all mini, you already see it, and basically there is like, I guess it's even this link here, and you can directly download this GGUF file then from this website that this points to. Okay. The same thing for the other model. The other model is the LLAMA 3.2 model. You also find this on Hugging Face here in 6-bit quantization. It doesn't matter, these models are really small. They are designed for the practicality of this course. I'm running this here on a very slow machine, which is basically my little laptop here. This runs on the CPU. In general, you want to run this on the GPU. You can look up on LLAMA.CPP how to run this on the GPU. It's very easy. You just provide one more parameter, the NGL parameter minus NGL, and then you tell it how many layers you want to run on the GPU if you have compiled LLAMA.CPP with GPU support. Here we will just run LLAMA.CPP as it is, and we will use it basically as a REST endpoint so that we can build our API in Python, and then we do this live coding session about how to build basically the reg. So let's run these two models in order to perform this a bit more easy, and to also keep the log going on from these models. Basically what I will do here is I will start the terminal multiplexer, so you can download also this program, which basically allows you to have multiple windows in a terminal and run things at the same time. So I will call here the LLAMA server, and as I call the LLAMA server, basically I want to have first this embedding model. So we set the all mini GGUF file basically. And then as this basically I have to define here the host, and I will say the local host. It's better to specify the IP address, because otherwise it binds to the IPv6 address or something like this, and then you can't forcibly reach it. So in this case I just bind it to this IP address, and I also will tell it to which port to bind. So I want this at 8082 to be my embedding model. At 8081 I will run then the LLM model. Just to point this out, and this is an embedding model, so we have to tell it embedding, so then it launches in the REST API the embeddings endpoint for this model. That's basically all that we have to do here, and we start this, and we see that the computer basically loads this model and runs it basically. So we see here it's serving basically the model at this endpoint. This is exactly what we want. And right now I type Control B C here in Tmux to create a new window. For those who are not familiar with this, you can create windows like this, and then with Control B W you can switch between these windows. That's basically how it works. It's, as I said, a multiplex terminal then. So let's run the LLM model. So here again with M, basically here I want to select my LLAMA 3 model. This is the file that I downloaded. As this machine only has 6 GB of memory, and we're recording the video and doing many things in parallel, basically we just use these small models. It's a 3 billion model, which basically just is enough in order to generate some text. But as we do the reg, well, we want to talk to the PDF, no? That's the way it is. And to you basically to answer us with context, and this is what we want to do. So we have this here, and I will say, okay, I want to have a context window, and the context window I will limit it for this machine in order to answer a bit faster. So I say of 10,000 tokens, not to make this too large. And let's say the host, again, it should be 127.0.0.1. And as the port right now I use the 8081 port. Okay, so the LLM runs on the 8081 port. The the embedding model runs on the 8082 port on the same machine, hosted by the same engine, just different models. Basically, the run one yields the embedding vectors, the other one basically yields tokens that then basically give some text out. It's as easy as that. I run this here and I have my second model starting up. And while this is starting up, we can basically already begin to code. I will just check in a new terminal here where I have my text. So I have this in this downloads folder right now. So as I said, I have the PDF file, I have the text file. And as this is in this downloads folder, I will start here in parallel while this loads the model here from the disk. I will start in parallel basically a Jupyter notebook so that we can start to code. Yeah? So Jupyter notebook, you already know these stories here. And as I typed this, basically the LLM also started to serve basically at this IP address with this port. So this is where basically you can host LLMs anywhere you want, just by downloading them from Hugging Face and starting LLAMA.CPP. And if you go basically to this website, you get even a web interface in order to talk to the LLM, but not with, of course, not with the reg. So just to show you this quickly here for those who don't know. And here I could type in ChatGPT fashion my message and I will get answers to that. Let's close this again. Let's build our reg system here. I run my Jupyter notebook and we will do basically a live coding about this story here. Okay. So Jupyter has started at my machine. This starts a bit like this because it believes that Emacs is my browser, but never mind. I just copy the URL, bring it into the browser. We yank it here and we have our Jupyter notebook. This is probably the environment that you are used to. What I want here is basically I want to create a new notebook, a Python 3 notebook. And basically that's all I need. So what you need for this course basically is, normally this all uses kind of standard libraries. We will use, besides that, the pandas library. Just look up in your distribution how to install pandas. It's very basic stuff. We will not use any fancy libraries like LangChain or etc. just to basically get you an idea how the reg works. And then you will see that basically in the way we do this here, it gives you many more insights. And it allows you basically to build your own reg. So what we want to do basically first is, for the sake of simplicity, I will just say that my IP address is, as you all know here, my local host. So I will just write this down as 1.1 or 1.7.0.0.1. And then I want to say that basically my embedding port, as we found out, is 8082, and then my LLM port is 8081. So this is basically what we got by starting these servers on the command line just beforehand. So I've defined that, I have my IP addresses, I have my stuff here, and right now we want basically the first thing that we want to do basically is we want to wrap the text that we have into small slices. So as I said before, what we do is we take the text from this document, from this PDF that we have, and we cut it into small slices. Why are we doing this? Because then we can, for each slice, basically we generate an index in a vector database. So the vector database in this case would just be a data frame, a pandas data frame. And that's basically it. So we will first wrap the text into the small slices so that if then the user asks for a query, the query can be answered from these text slices. So how does this look like? In Python, by default, there should be something like textwrap. You can use this library import wrap, which allows you to wrap text into small slices. So I open my text file. it's something like this. I hope it auto-completes. That's nice. So basically that's the file that we want to open. We just want to open it as read. And basically if I do something like this here, fread, it reads the whole text file into this variable here. And then we want to have the wrapped text. And the wrap text is basically wrap everything. And I put here slices so that it fits both into the embedding model and into the LLM model. So the LLM model has a way bigger context size, but this is a very small embedding model. I'm not sure about its context size. So just to make sure that it works, I will wrap it into 1000 characters. Yeah? So basically what this wrap text does is it searches for the next space just before 1000 characters, and it cuts the text there. So that's the whole story. So and once we did this, we will close the file again, and then we have our wrap text. Just to show this here, if I take the first basically slice of our text slices, as we might call them right now, we see that this here is the first slice of 1000 characters, and we will then load these slices automatically if a query is asked about the text, or if a query is asked by correspondence with this cosine distance as we talked about it, and insert them in the prompt, which we will then feed to the LLM. Okay, so fine, so good. What I want to do right now is in the next step is we have basically to show how these endpoints work. So how the how the embedding endpoint works, and we will program the embedding endpoint. So how does this whole stuff work in Python with REST APIs? For those who don't know, you can use basically a library request. So I will import requests, and then we build our URL, and as I did this very generic up there, we will call this here so that you can quickly change a server. So this is basically my IP address, and then I need to specify the port. So here I'm just chaining together strings into one string. So I need the embed that we defined above, and then this stuff here, it uses the so-called embeddings endpoint. So you see how the URL basically is composed. So it's IP port slash embeddings. That's the way it works. And then we need basically a payload. So our payload should be a JSON file, but here we can just design the JSON file as a dictionary, as a Python dictionary. So this is the content, and basically for the content, let's just generate an embedding for the wrap text that we have above. So we call this wrap text 0. This is the payload. This will be converted into a JSON. It looks like exactly as it's written down here in JSON. And we make our REST call. So I will call response with our ESP, and I will use this requests library in order to make a post request on this HTTP URL. And I say, okay, this is the URL, and then I want to have JSON. It automatically converts this to JSON. And I will say this is the payload. And so if you want to know more about this API, you just have to go to the LLAMA.CPP website and check out the API. The API, they also have an API which is basically OpenAI compatible. So in theory, you can switch out basically what I show you here for different, as I said, different providers of LLM services to build your own RAG locally and then send your data to this machine somewhere on the web to people who provide you these services without running LLAMA.CPP somewhere. Of course, you can use better models just with LLAMA.CPP in-house if you have the GPUs and things like this available. Yeah. So this is basically the endpoint, and then we get back a JSON, and I will call this the embedding JSON so that we can look at it. Embedding JSON, and this is basically the RESP JSON again. So this is the response basically that we get back formatted as a JSON parsed into this embedding story here. So if I do this here, if I run this, hopefully we get an embedding. So this is run. If we look at this embedding JSON, it looks like this, and what we have to see here is basically how we access this. So what we're interested are of course these values here. This is the embedding, so this list, in this list here we see there's an auto list, there's something called index, there's an entry which is called embedding. This is the endpoint, so basically the point that we want to query from this dictionary here, from this list of dictionaries. And anyway, there's only one coming back because we only sent one. That's basically how it works, and you see that this here is a list in a list, and it's a bit complicated how to access it. You have to wrap your mind around it, but it's on the end it's not so complicated, let's say it like this. Okay. So what we want to do here, we have our embeddings endpoint, as I said, and we want basically right now we want to build our vector database. So we have our text slices. From our text slices we will build a vector database. That's the next step. So this is basically just what we did above here, wrapping this in a for loop, building basically embeddings for all of these and storing this somehow in a database. Yeah. So how will I do this? We'll use the same URL endpoint, so I don't have to write this again. But I will write here embedding. Basically we want to have embeddings. So we want to have a list of embeddings. For each text slice I want to have one embedding, and then I want to build a database, the text slice next to the embedding, and then I can query basically this database. Yeah. So what I will do for each text in wrapped text, so this is basically the list that I got from my text wrapper pack. Of course, here we have no overlaps in the text in general. You could also build overlapping texts in order to make this more elaborate. I guess it's not needed right now. Basically, there are many things that you could improve on this. This here is just a small tutorial in order to get you started with RAG, and in order to see basically how you can implement your own RAG rather quickly in Python. Yeah? So basically we have the payload again. So the content is the text here. Yeah. So for text in wrap text. Okay. The response is just as before. Requests, post, and we basically post our payload again. So to the URL that we had already, and we do the payload. And then we get our embedding back, and then it's the question how we parse this embedding. As I said, it's not so evident, but of course if you think about it, so one embedding, what does it look like if you look at this array here? So it's basically a list, so we have to go into the list, then we have a dictionary. From this dictionary we want the embedding endpoint, and this embedding endpoint basically gives us a list in a list. So we want just to have this one item from the list. So how to do this? In Python this looks a bit like this, and I will directly put this into a numpy array, so that I've shown you basically in the slides the cosine distance, so that we can use the cosine distance together with it. Yeah. So we will use embedding JSON 0 embedding endpoint and 0. Okay. So this is basically how we pass the structure that we get back from this list. So if you think about it, the first item from this list, so everything is embedded in this list. So the first embedded item from this list is basically this. Then we go to this embedding endpoint, and here we have a list in a list. So we also want the first item from this auto list in order to get the list of our embedding values of our vector basically back. Yeah. And then we pass this vector directly into a numpy array, and this is how we get our embedding. So fine, so good. We append this to our embeddings, and then it comes in the same order as these texts go in, and that's basically what we want to have. I will run this. I hope I have everything I need for that. I guess so. let's run this here. And here it says request is not defined because I wrote REST requests. Things like this always happen, especially in live videos. And here I missed the numpy library, which is also import numpy. You all know this as np, and then we have it, and it's running. It takes a lot of resources. I'm surprised. So this is basically the embedding model here running on this machine. As the machine is a bit slow, it takes some time in order to get these embeddings back. In general, as we have the Tmax here, we should be able to kind of see this here working. And we see here, yeah, it's got the request, it posts the embeddings back, and probably it finished. So basically we can watch here how it got each process. So you see always post every time when it processed an embedding. So fine, so good. So this finished here. So let's check out our embeddings. And what I will do, I will not prompt them, but I will kind of check how many embeddings did we get back. So if I do this here, we get 53 embeddings, just to check if this is the same thing as our wrap text. And that's perfect. And then, so we have for each slice of text one embedding, and then we want to check how large one embedding vector is. So let's do this like that. And basically we see, no, that's kind of strange. Basically what I wanted for the embeddings is that it is the size of one embedding. But okay, I see I made here a mistake. I should have written here embedding. As you see, so one embedding should be appended, not the embeddings themselves. Otherwise, of course, this will not work. So let's do this again here. Let's run this again. Of course, this is initialized freely. And here we see basically how it requests each of these 53 while it runs. Now, sorry for this mistake. So you also see exactly how you can mitigate your mistakes in doing this here. What we want here basically is we want right now to check out the length of one embedding. And as I do this, I get 384. So this is exactly 1 for 1. So basically we have 384. This depends on the embedding model, of course. We have the simple embedding model that we've chosen here, which yields us 384 floating point values for the embedding. So as you see, we get one embedding back. We add this embedding to the embeddings. We have our list of embeddings, which is the same size and is in the same index basically as our wrap texts. And right now we want to kind of to build a database from the texts together with the embeddings. And for this we will use basically the pandas library. So how do we do that? That's also straightforward. So we import pandas.CPP, and then we build our vector database, as we call it. Let's call it like this, and we see this is a data frame. And here from this data frame, basically we have the texts. Call this here text, and we will make this the wrapped text. So this is this 53 entries, 53 slices of text that we will use as our vector database, and then we have the embeddings. And so this is this embeddings list that we have here. And when I run this, I created my data frame. So if I go here and I do vector database and I show the head of it so that we see what this contains basically. So we see we have the text and the embeddings basically that encode this text, and then I can query basically this table with the cosine distance, so between a query vector and these embeddings, in order to get the corresponding text back. Yeah, it's not that easy because what we want to have basically is we want to have the best answers. We also want to basically encode one query in order to compare the query semantically to this embedding. So each query basically has to be encoded into an embeddings vector, then semantically compared here to an embeddings vector, and then we get basically back the right answer from this table. So things that we need to code right now. So let's start with the cosine distance. Let's define the cosine distance so that this makes sense here. And as this is all in numpy, easily chosen, so we have one embeddings vector and the second embeddings vector here designated with A and B. And we want this to return basically a floating point value. 1 minus, as I said, you know the formula, so np, the dot product, numpy, the dot product between A and B. And this here, basically, we want it to be divided because we're not sure if these embeddings are normalized or not. I guess they're normalized, so we could save this, but you're never sure. So let's basically show you the normalization formula. So this is, of course, np dot a in A. The square root from this times the square root of np dot b in B, yeah. So this is the normalization part. If you have normalized vectors, you can get away basically without the square root parts. I just keep them for completeness, and so that you get an idea about how the reg works. You see, this is here for Python rather efficient because we can use this numpy dot product basically in order to build this. Also, the normalization is basically done by this dot product here and the square root of it. If I define this from here, I guess I could use the numpy square root. The way I defined it here, I have to import from math. I have to import the square root, so that this works basically. So we have here the cosine distance, and then basically we want to use this cosine distance in order to find best answers from our vector database. Yeah. So how do we do this? So let's query the vector database. How can we do this? So let's call this best answers, and we say, okay, we want n best answers. How many best answers do we want? We want to have a query. The query in this case is a vector, so it's just this A and B up there. And then we want to query a database, so our vector database that is up there here, yeah. Let's define this like this, and we say, okay, what we will do basically is we will generate a list of distances, so we will compare the query to all the distances basically that are here in our data frame. And the story, what we want to do basically is we want to add basically all the distances to this. Basically, we create a new column with all the distances between the query and the answers, and then we will use just pandas data frame features in order to find the smallest distances, order the whole data frame by the smallest distances, and yield us basically the n smallest distances back, and then we basically have the texts that we can add to the prompt. Yeah? This is the whole story what we will do here. Okay, so how do I do this? For I in range, let's say here the length of the vector database, so because basically I need an index, and for each basically I want to calculate this distance. Yeah, so I will call here distance, so I will add this distance directly to this distances array, so I will call here distances append, and what will I append? The cosine distance, and here between the database I call it, and here this is called embeddings here, as we see. So we say embeddings, and then we say, okay, the I embedding, and then I compare this to my query, and this is basically all the distances that I append to my data frame. So right now let's build this extended data frame, so without modifying, of course, the original database. So we do this here, local database is the original database, so the vector database that we have here as an argument to this function. And we say the local database, basically we add a column, so the column is called distances. Okay, and we say this is our distances that we want to add, that basically it's the array that we have, also, sorry, the list that we have generated above here. And then we want to find the basically the rows with the smallest distances. So how do you do this? This is the easiest. This is right now a pandas data frame. So I will just overload basically, or reload this into the same local database story here, so that I can yield this then from the function. And I will see this is local db, and basically I can use this n smallest a method of a data frame and say, okay, n here, and I want to order this by distances, and then basically I get the n smallest, so basically the rows which contain the n smallest distances back, and I store this in this local db story here. And then we want to return this and say, okay, we return this directly as a list, and we only want to have the texts because that's what we're interested in. Yeah, so the texts corresponding to the shortest distances calculated by the cosine distance between the query vector and the vectors that we have in our data frame. Okay, so fine, so good. Here are the vectors in our data frame. Here we have a query vector that we build from the query that the human enters into this story here. This will be kind of the next stories. Yeah, so let's hope I didn't make a spelling mistake. I hope not. Let's evaluate this. Right now we don't know it as we don't run the functions. If we have made a mistake, we will see this later. But basically the story is right now, as I said, we need this query, and this query of course is already a vector, so we need to encode the query by someone into this query vector. And what we will do here basically is, the way this is done is basically the query, it can be rather long. So let's imagine someone pastes in a whole page and says, okay, look, this is my query, and the query is of course then longer than our let's say in our context window of the embedding model, and of course this doesn't work. So basically we also want to wrap the query into some kind of wrap text, as we did it like here, and we want to get embeddings vectors back, but we only want one embedding vector, yeah, because we can only use one embedding vector in order to query this. So what we will do, we will just add up these vectors, and as we add up these vectors and then renormalize it. And why does this work? Well, with embeddings this kind of works, because let's say you have the embedding of the word king and you add the embedding of the word woman, then it should kind of, in general, that's the way how embeddings work, yield a vector which points where queen. This is kind of the idea behind these embeddings in general. Not always works like this, but in general we can use this kind of theory here, and that's what we will do. So we will add up, so we will wrap basically the query of the user to the LLM. We will wrap it into short text so that they fit into the context window of the embedding model, and then we add up these vectors and build one vector so that we can query our vector database, find the corresponding documents, and put them into the prompt of the LLM. So enough talking, let's get started. So we call this encode into single embedding. I will call this function here. And I have my in-text. Yeah, so this is basically the text that is provided to the story here. So again, we have locally here embeddings, because we have multiple texts with multiple embeddings. We have our wrap text. You already know how this works, so we will make wrap, and then we will say in-text and then 1000, so that it fits into the embedding model. And as we do this, of course, then I need to do 4 texts, because we want to add them all up in wrap text. If you also notice, I have to query the embedding model. How do we do this? We build the payload, we make our REST query. You see this already for the third time. but that's part of coding basically. So let's do this content text. We have our response. We make our request to the embedding model that's running in background. We make a post query. We say to the URL, because the URL is still our embedding model. We say JSON, and the JSON should be the payload that we built up there. That's basically how it goes. We get the response back. This is our embedding JSON. We say it's the response from this here. We use this call here in order to build this up. Then we get our embedding back. We already know how to handle this, so we said this is a numpy array, and we know how to parse this. So embedding zero, because we have shown above how this works. Embedding endpoint and then 0, no? That's as far as it goes. And then we want basically embeddings, and we want to append the embedding, no? Okay, so this is how we get our embeddings. Right now we have to add them all up. So in order to do this, we will use a numpy array that we initialize with 0, which is the length of one of the embedding vectors, and then we add all the stuff into this numpy array, so that this kind of is a bit faster. So we do here embedding, basically I need the embedding length. So I will do this like this, and the lengths, of course I get it out. They're all the same lengths, but I need to query at least one. We found out that it's 300 something, as we saw it above, but this is basically what I want here. And then we call this edit embedding. So this is where we will add up all the embeddings, and we start with np zeros, and we put here how long should this vector be. It should be embeddings length long, and it contains all zeros, and then we will basically just add up the others into this one. Yeah. So far so good. Then the add up stage. So for e in range, you already know it. Len, we can use here embeddings, and we can say basically edit embeddings. Then we can use a numpy story here, so we can say basically numpy add, and we can add them all together. So we say edit embeddings, and then embeddings, and then we want to have the I embedding, and they're all added up together here. And then we have to normalize this. How do we normalize our edit embeddings? So we use edit embeddings, and we say so you have just seen how to normalize a vector above. That's very easy. So we use the square root of the dot product of edit embeddings times edit embeddings. And as I go very far here, I will just kind of do a line break here. And this is correctly indented in Python, and we want to return our edit embeddings. That's how it goes. Okay, so very easy what we do here. We query for each of these in-text basically, and then we get a single embedding back by adding them all up and normalizing the vector. That's as easy as it goes. Yeah. If I didn't do a spelling mistake, I hope that all these three functions, they work together. We will find this out in the end, but let's just try this one out. So let's encode a typical embedding. So encode into single embedding, embedding LE into single embedding should work like this. And then we can say something in this article. It will be about, I don't know, how the Omicron variant of COVID basically has replaced the Delta variant in France during this COVID period. That's basically what the scientific article is about, that I've transferred from PDF to text. And we will say, what about Omicron in France, something like this. And let's see what this looks like as an embedding if I ask this question. So as I said, these embeddings basically, they should embed the semantics of this story here. Here I made a little spelling mistake, so we will correct this. And if I do this again, hopefully we get an embedding. No, another spelling mistake. So we have here requests, not request. Okay. Here it's embedding 0. Right now, slowly it should be fine. And we get our embedding back, hopefully. And if I go here to encode, we see we have our embedding from the question that we asked. Basically, so we can encode basically any question, any query. If this query is of course longer, it will renormalize according to the story here, add these vectors up, renormalize and give just one vector back. And this is our encoded embedding vector, as you see, yeah. As easy as that. Right now we can use this encoded text, of course, in order to get the best answer. So for some fun, I will call this here the Überbest, and these are the best answers. So the function that we have written just before, and let's say we want to get 5 back for encoded from our vector database. And these are basically the documents that we will send to the RAG. This is how the RAG works. So the user asks a question just like the question above. You query the database, which is a pandas data frame. You get the 5 best back. That's how it should work. So we will query this. If we have made, I called this here, how did I call this? Encode. So I did call this here encode. So let's rename this to encode. And then we find that I made here spelling mistakes. So it's not the cosine distance, but the cosine distance, of course. So let's find this here. Hopefully this was the only mistake. Let's re-evaluate this cell so that basically these functions are correctly stored. And we see we get here the Überbest, it's called. And the len of the Überbest is hopefully 5. And if we want to get basically the first embedding, which should be not the first embedding, but the first text slice back. So right now we get the best text slices back according to this embedding model. Of course, not all models perform equally well. This is a very slim embedding model, so just that you get an idea about this works. In practice, you have to test your embedding models if they basically give back the right context for your system, yeah, that you built. So I get here basically the first, they say, okay, this is kind of the first answer to this question with this Omicron. You see that Omicron comes is several times here written inside. So it believes that this is kind of the best answer according to this article for the best part of text that I should kind of add to my RAG, to the prompt when I will build basically my RAG. Okay, this is kind of the story here. Okay, so right now that we have this, we still have to build our prompt, and in order to build our prompt, you have to look at the chat template. So we remember in the PDF I've shown you the chat template for the Llama 3 model. Maybe I can bring it up here. Maybe not. We have, you remember from the PDF, we have this system message here. We have this system message start, and basically here with this system message, we will show that this system message basically is the start. You remember we had this start header ID field here, and then we have system, and then we have end header ID. Okay, so this was basically the story here, how to start the system message. Okay, and we want to have this basically in our IPython notebook like this. and then we want to say, okay, slash, so this /n, of course, this will create new lines for the LLM. So basically here I want to have my system message, and here what do I do in a system message, as we pointed out, where we will describe how the LLM will interact with the user, and we will describe basically how the LLM how the LLM answers, in what kind of language it will use. And we will add, of course, as this is the rag, these text slices here to the system message, so that the system knows, okay, I should answer with the context that is given here. Yeah. So let's define how this works. So you are, let's write this, you're a helpful AI assistant, something like this. In answering prompt, so it should answer fast. Let's make this a bit longer, and you should take into account, of course, the following context. So the context are these text slices, and of course, as good as you can as you answer. Let's make it like this. Okay, so this is our system prompt, and then here beneath that we put the context. Yeah, that's basically the story. Yeah. So let's make this here a double point, maybe then it works a bit better. It's very easy. So this is basically the system prompt that we have. Okay, so the start of the system message, because here we will insert, then when we build the final prompt, we will insert these text slices that we query from our text database according to the user message. Yeah. So the user message is basically this end of turn. So we do here the end of turn, we put it here in front. We do this just for programmatical reasons. So basically normally it ends after the system message, it's terminated with an end of turn, so that it knows something else comes up right now. But I do it here programmatically, so that I can basically insert here these slices, and then as the user message starts, it gets this end of turn, and it gets this start header ID again. This is how this works with LLAMA models. With different models, you have different tokens basically in order to work with this. Yeah? So this here is the user message, but basically this is called the chat template, and you can find it for your model if you want to use a different model than a LLAMA model. But conceptually, basically everything that we do is the same also for different LLMs. Yeah? So this is basically the start of the user message, and then of course we want to add here what the user types in the prompt. This is as easy as that. And then we also have the assistant message, because here we have then again we start with the end of turn, so after the user does this, and basically what we do, we yield the start in the prompt, so that the LLM, basically the LLM is just a completion mechanism. Yeah. So otherwise it would kind of complete the user message. Yeah. So we have to yield the start of this assistant message, and then it automatically knows right now it's its turn, and it will start to talk. Yeah. So we do start header ID, and we use here assistant, and we say okay, and header ID, and we do this here, and as we have this basically is we put here the prompt counter, and the prompt counter is 0, and then we put the prompt and we say the prompt is basically this empty string right now, okay? So what do I do with the prompt counter and the prompt? Basically here I built the final prompt and I want to add up basically these all the strings, yeah, so I start off with an empty string. I'm not sure if I will need this, but I need the prompt counter because basically the first time I call this, I want to query my vector database for contexts and then basically talk about this context. So I will of course you can build a reg where the system message changes all the time and where the context changes all the time. This is not what we will do. That's a bit more complicated. I mean, more complicated conceptually, it's the same, but for the sake of simplicity, we will start off here with a reg. We query once for the first query given, and then we talk about it, and we keep the history of user messages and assistant messages that stack up in order to build a prompt, okay? That's the way it is. And I need this prompt count, of course, that in the first time, basically the user asks his query, that I query the contexts and add them to the prompt. Something like this, okay? So fine, so good. There's a syntax error. How could there be a syntax error? I guess it may be here. We don't need a new line here. It's fine. Okay, so right now, let's use these text slices or these text templates, this prompt template, let's say, call it like this, because that's basically what it is, in order to build our final prompt. So build prompt from, and then already from a query, yeah, so the query in this case will be a text query, yeah, so we have n, how many slices I want to get back. I want to have the prompt because we want to kind of slice through the prompt so that if I ask a second question in order to build the conversation, so that I can just add basically the new story to the prompt, okay? And then we have the user query, okay? And that's basically then the function that we want to define here. And then we will build here basically, we have global, this is a global variable, so I will call here global, that's the prompt counter, okay? And then I say if prompt counter, if this prompt counter is 0, basically then I want encoded, encode. I use this function that I've built before, so we will encode, of course, our query into an embedding. And this is, we do this with the user query, which in this case is text. Yeah? So this will be the query for our vector database. Yeah? So if I have this, then I want to get, of course, my best results back. I call them überbest. Okay, so these are the best answers. And here we have n best answers from this encoded, which is the query, which is the vector query, basically to the vector database. Yeah? And we query the vector database and get these best text slices with this function that I've coded before back. Yeah, vector database, I called this, okay? Nice. So right now we have this, and then still if prompt equals 0, I want to build a new prompt. So what I will do with the prompt, so the first thing is we want to have the system message start part, okay? So we start with the system message, and then as I said, we want to add basically what we got back here, so we want to add back this überbest slices, so for I in range, how many do I have? N, hopefully, and then we say, okay, the prompt equals the prompt, and we add basically here so basically we add a new line, let's do it like this, and then we add überbest I, so we have these n slices basically that we have here. Yeah, we have 2 new lines then, I guess, but that's fine. This way, okay? And then, of course, after the system message, we continue with the user message, so it's the user query, okay? So we have this user query, we have our context that we add to the prompt, okay? And right now, of course, the LLM also in the prompt wants to have the user message. So we use this user message start that we have defined above. And then we will just add a new line. I have already a new line here, but that doesn't matter. Let's add another new line, so to have a bit fun. And we say prompt equals prompt plus user query. So right now I have this here, and then I add a line which is basically not one line, but which is the whole query that the user basically asked, yeah, as a string. And then we say okay, we terminate this with a new line here. And then we have again the system message, because as I said, basically because we want the LLM to answer, yeah. So the LLM to answer basically did all this, and then it knows, okay, the next token will be the answer of an LLM. It sounds a bit strange, but as I said before, the LLM is just like a token generator which generates tokens according to what it saw as the input in front of it, yeah. And it kind of says, okay, the probability to after this is basically the answer to the question before. This is the way it was trained with this kind of tokens in order to gain some control in how the messages are built, yeah. That's basically it, yeah. So this is for the first case. Right now for the other cases it's a bit more simple, because I don't need to query this system, basically these answers from my vector database. So we just basically add this all up here, just as we did it here, because we already have a prompt. And what I want here basically is I want to copy and paste this here and say, okay, this is what I do in the other case. And then of course I want to increase my prompt counter. And I want to return the prompt. Okay, the increase of the prompt counter works because this is a global variable up here. Okay, in general, if I didn't make a spelling mistake, this should work. Let's run this here to define this function. Okay, right now we know how to build this prompt, basically. That's very easy. Right now we need to query the LLM. We have to send the prompt to the LLM. We will also do this in a function, and then we will write the final chat function which will implement our chat. Okay, so how do we query the LLM? We use this REST style story here. So we do get LLM response, I will call this. I guess I will not need how many we have here, but let's keep it for consistency, maybe. Doesn't matter, yeah. Prompt. So we need basically these tokens and the prompt. So the tokens will be how much tokens I want to get back from the LLM. And if I set this -1, it should give us basically until the end of turn tokens comes up, then the machinery, so this LLAMA.CPP knows that it has to stop, yeah, otherwise it will yield infinite tokens, kind of the story here. But I can say basically -1 until the end of turn token, or a number of tokens that it will yield if the end of turn token did not arrive before. Okay. So the URL is basically http / and then plus IP, the IP address that we have. Then here, so we built this just like that we built this for the embedding endpoint, but here we will use the LLM port, of course. And then we have the completion endpoint. Yeah. So as I said, an LLM is nothing else than a completion engine. It's not something that really thinks. It basically adds text to text that is already there, and it was trained in a very fancy way with this kind of control tokens in order to simulate a conversation. Yeah. Okay. So the payload here is a bit more complicated. So this dictionary here looks like this. Prompt. Yeah. So what will be the prompt? It will be the prompt that we put in here. We just make sure that this is a string. Of course, this is a string, but in order to make this function a bit more safe, let's say it like this. In predict, as I said, this is the number of tokens that we want to have here. So these are the tokens that we put in here, how many tokens we want to build. And then we have basically stream. The stream is basically, normally you want to have the stream, but here we don't want to have it for simplicity of things. What the stream basically does is it basically yields token by token back. Yeah? In this case, we just want to get the answer when all the tokens have been generated, for simplicity of reasons, because otherwise we would have to build like a callback function, what to do when the LLM sends back one token and then add each token after each token. In general, you want to have the stream, because then especially for slow LLMs here on this machine, of course everything will be rather slow, but for slow LLMs in general, what happens is that this kind of adds to the interactivity, because the user kind of sees how its prompt is built. You saw this at the early stages of ChatGPT, how each token each word built up like syllables, token by token. Here we don't do this, here we just yield the complete answer. Yeah, stream equals false. Okay. The answer, so basically you know already how this requests API works from before. So we use post, we use our URL that we have built up here. We say we have a payload, JSON payload. Okay, we have an answer, and this answer is the response with this JSON function here. And then we return this basically here in the answer. If you look at it, this is a dictionary, and we just want to have the content. We don't want to have the statistics and all the things that basically the LLM provides. Yeah? That's how we get an answer from an LLM. It's as easy as that, if you know the REST API, how this works. Okay, this is not called requests, but requests. It should be correct right now. We have our function. Once we have our function, we can build the chat, and then if we didn't make any more spelling mistakes than this, hopefully everything works. So we will say, okay, we want to have 5 documents. We want to have a message. So my message basically is, okay, what do you know about the Omicron or the Omicron variant in France? Something like this. Okay, and then basically we want to have something like this now, so that we have prompt chat, we have this n here, your message, and as I said, we always, as we want to keep the history, we want to keep the prompt, no? So this is kind of how we want to build our chat. So let's build this chat message. So let's insert a cell above before we can evaluate this, just as a sneak peek. And let's define this chat message. Yeah? So the chat, how do we do it? N user message and prompt, no? Something like this. So let's build the prompt. So how do we build the prompt? That's easy. Prompt. The prompt is basically built from query. And we will use here n prompt user message. Okay. As you see, the whole story about the rag is getting strings together, building the prompt with basically some data that you retrieve, and adding everything together. Yeah. So we have an LLM answer. And basically we have get LLM response, and we have n. Do we want to have -1? It will be slow. I hope it goes fast for this video. Prompt. Okay, so -1, what did I say, is yield tokens until the end of the untoken array arrives. Okay. Okay, we have the prompt, and the prompt is basically add. Here basically we want to add the LLM answer. Did I program this actually? So I need add LLM answer method quickly here. Let's add this above here. So this is just one more function that we need. So basically when the LLM answers, we also need a function which kind of adds the assistant message here so that we capture the history of the whole story. Yeah. So let's do this quickly. How will we do this? This is very easy. We just kind of add the answer to the prompt. So this is very easy. So we do here def add LLM answer, and we call this. So we need here prompt LLM, the answer from the LLM, and we add it to the prompt. No, because basically, as you see, the assistant message is always the last. So we just add it to it. Very easy. Prompt equals prompt plus LLM answer /n. Okay. Return the prompt. Okay. As easy as that. Okay. I have to evaluate this, otherwise it will not work here. M answer, and I add here the prompt to the prompt, and that's basically it. Yeah. LLM answer. What else do I need? Of course, I want to print the LLM answer so that we get some feedback when this comes here, and we want to return the prompt in order to get our history done. Yeah. Okay. The prompt goes in. It builds the big prompt. It queries all the supported documents, and right now we can chat basically with this text document that we have provided to the whole thing, if everything works. Huh? So all our functions shall be defined. Right now the big question is, can I evaluate this and will get something back? So let's start. And we already have an error. Your message, prompt your message. Yes, your message. It makes your message. And then we have, okay, in line 5, what do you know about the Omicron methods? So the chat is defined, but what's the question here right now? Okay, build prompt from query, and in this one we use system message start, and this is system MQ start. It should be system message start. That's here the error, so we have to rebuild this. Then we have probably to rebuild this one here. So because it has here the build prompt from query already, and right now if I run this with good luck, so the LLM speeds start, we see that here my CPU cores, they're so, and we see we have received our answer here, and as you see, it took the context into account, and it took quite a while. So that's the way we recorded this. We see basically that these answers are basically in context with the article. Yeah, this is actually what we wanted, and it comes from the article basically, the answers, which is perfect. So with a very small LLM on a very small machine, you see that this kind of yields kind of really good answers with this type of array. That's what I wanted to show you. So we could, of course, right now run this again with a different message and wait a while. As on this machine it's really slow. I will not do this, but you can do this at home on your machine. And in the end, I suggest you basically that in the last cell that you have basically, that you do something like this, that you write down prompt, and then you can see how we built the prompt with all the context. So this is basically how it went. So you have the start headers, you see basically here the description, you see the context, somewhere you should see our user message basically, so it's here, the user message, the question that we asked, and then you basically get the answer from the LLM. And then of course, if you would continue, you would see a longer prompt, so you can do this at home. You can basically run this here with a different message a second time, and then watch the prompt again and see how the prompt basically is bigger. I stop it for here. I think this is a decent overview about the whole reg. I hope you like this video, which will be a bit long. I will probably provide maybe this document as with the video. We will see about that. Just check out under the video in the comments to find probably this document here that we have built here together. I hope you had fun with watching it. Have a great time.